Hello again, statisticians. Back here with the second lesson of the T procedures unit. This is an introduction to T tests, following up on our introduction to T intervals from the first lesson. So a couple things here to take away would be why are T tests necessary, and kind of how do they relate to the intervals, and then the 4 steps to a T test. Unlike the interval, the 4 steps are all required on the test. So this is a little different where it's on the interval, they were typically 3-point questions because of that first optional step of identifying the parameter of interest. But this time, hypotheses make this a more essential first step. So let's jump into it here. Just a reminder on the T distribution, again, it's bell-shaped. It's a lot like the normal Z curve, but it's a little wider because of S having to estimate sigma. So again, it was this idea that Z may have looked like this, where the T distribution looks a little more like this and is ever changing based on the sample size. So if the sample size is bigger, then it gets closer to the Z. Because as N goes up, as N increases, our estimation of the standard deviation gets closer, just because we're basing it off of more data points. So that is why the T gets closer to the Z. But again, the reason it's not exactly is because the T relies on a sample standard deviation, whereas the Z relies on the population standard deviation. So why a test? It really kind of depends on what our goal is when we approach a sample. So a confidence interval is more about just trying to estimate where the true mean would be, or the true proportion in the proportion unit. It really is about just throwing a dart at it, whereas a test is really more about testing a current belief around it. So for instance, I may claim that the average height in our high school is 5'8", and we're going to test to see if my claim is supported by the evidence, by the data. So a test really starts with a hypothesis, or an establishment of an idea around the mean or the population proportion, rather than just being that throwing a dart at a blank slate like an interval is. Ultimately, really, our goal is to reject the null hypothesis. So when we look at this evidence, we either reject or we fail to reject. And fail to reject just means we didn't have enough evidence to state, to disprove the original claim. We're not saying the original claim is exactly right. So for instance, if I say the average height in our building is 5'8", and we get a sample that's 5'8 1/4", that might not be enough to reject mine, but that doesn't necessarily say that 5'8 is correct. What we're really just trying to do is see if we're in the ballpark, or if we are, if it's statistically significantly higher or lower than the current belief. And so we'll see that here. Okay, so here's the example again, going back to the social media. Sorry, I had to make a little correction here on the actual question, but again, our sample size is 50. Okay, so n equals 50. That's our sample. The 96 minutes again represents the X bar, and the 23 minutes represents the S. And again, the X bar and the S, the whole idea here is they are X bar and S because they come from a sample. Okay. If it was our entire population, so if we took a census of all the MHS students, then it would be mu and sigma. But the idea of running an interval or a test is, again, we don't want to have to take a census. Okay, it's expensive, it's time consuming, it's difficult to achieve. And so what we do instead is we take a sample and we really make a statistically educated guess at the likelihood of an event occurring, or if it's an interval, the kind of range of values that are believable for the mu. Now the question that's asked here is if there's evidence at the 5% significance level. So again, that's that idea of that's our threshold. Once we get below 5%, we start to claim to have evidence for HA. In this problem, at least. In medicine, it might be below 1% because they really don't want to make a mistake with medicine. And And the question that's asked here is if there's evidence of there being more than 90 minutes spent for MHS students on social media per night or per day. So again, that question is highlighting what our HA is. So this is what we're trying to find evidence for here. Current belief might be then that it's just 90 minutes, okay, or that it's less than or equal to 90 minutes. Either one of those is fine. But what this is asking is, do we have evidence that it's more than 90 minutes on social media? And again, our sample says 96, but we're trying to see if our sample is statistically significant enough to show that it's greater than 90, because 96 could just be noise, right? The next sample could be 84, and the next sample could be 91, and the next sample could be 110, and the next sample could be 70, right? We don't really know for certain where these values are, so that's why we're testing. So the 4 steps, the first step is the hypothesis. And again, the hypothesis for us will always be, in this example, mu equals, and then the alternative will be mu is greater than, or mu is less than, or mu is not equal to, okay? And that will really just depend on the scenario. And so again, just a reminder for these 3, if it's greater than, we're looking to see if it's in this case, if the alpha or significance level is 5%, we're looking to see if we get something in the top 5%. This would be our what's called rejection region, and this would be our fail to reject region, okay? If it's a less than, then we just, on the same curve, we're looking down here. Anything in the bottom 5% would be our reject region, and everything else would be the fail to reject region, okay? If it's not equal to, this is a little different because we're actually looking not just standard deviations above or below, we're looking standard deviations away. So if we get a t statistic of 2, it really means plus or minus 2, even though the sample was greater than the mean in that case if the t was 2, because that's how many standard deviations we are from the mean. So what we do here, actually, again, using the same alpha 0.05, is we say our rejection region is now the 2.5% on each extreme, okay? So fail to reject would be in the middle, and these would both be rejection regions there. And we're not going to look at the not equal to now, but what happens is it causes our p-value to double. So again, if we get a test statistic of 2, where in this case we're looking at it, what are the chances of the t being greater than 2? Here it might be what are the chances of the t being less than negative 2? Here it's both. Probability of t being less than negative 2 and, or plus, probability of t being greater than 2. Now our calculator will take care of that. We just have to change the alternative hypothesis to not equal to. But that's what's going to happen is when it's two-sided, you'll actually get double the p-value because it's going in both directions, okay, with that not equal to, which we talked about in the proportion unit as well. So in this particular problem, sorry, I don't know why that formatting got weird, but what we have here is that the null was that it was 90 minutes, or again, you could say less than or 90 minutes, because the alternative is really what drives our work here, which is that it's greater than 90 minutes that students spend on social media. Now, the conditions very similar to what we had in the first lesson. First of all, this is a one sample t-test, and our conditions, again, are SRS, normality, and the independence within, which is the 10n is less than capital N, okay? In this particular problem, again, the question states, and I won't write it all again, but the question states, and then we quote it, okay? Random sample of 50 MHS students, okay? To the normality piece, N is 50 again, which is greater than 30. So the sampling distribution would be normal, would be roughly normal by the central limit theorem. And then again, 3, we took 50 students, which is less than 10% of the entire student body, because 10% would mean that there'd be 500 students total. There's 3,400 in our building, so independence within is fair to believe. Okay? So we check those conditions. Again, you can see that they're the exact same as for the interval, which is a little different than proportions. Proportions, the one sample conditions do change for the normality condition between hypotheses and intervals. Here they do not, because it's not based off of the X bar at all, like the other one was based off the p hat versus the p. Then we get into the calculation. Now the calculation looks like this. Okay, it's very similar. We started off when we first talked about normal curves, it looked like this. And then when we got into sampling distributions, it looked like this. And now you can see all we've done now is change the z to a t and the sigma to an s. And again, those go hand in hand. The reason we had to change the z to a t is because the sigma changed to an s. We still have the n-1 degrees of freedom, which again is something that's beyond the scope of this course in terms of needing to understand why that's the case. So for right now, we roll with that. We can talk about it in class, why that's like that. The test statistic formula, again, is going to find how many standard deviations we are away from the hypothesized mean, okay? And then this p-value definition. This is a very important definition, one that you should feel comfortable with. So the probability of obtaining our result are one more extreme, assuming the null is true. And of course, the lower that value is, the stronger the evidence. And again, that p-value, if it's a greater than alternative, it's the area to the right of our test statistic. If it's a less than alternative, it's the area to the left of our test statistic. If it's a not equal to alternative, it's in both directions from our test statistic. Again, and that goes back, there's the greater than, there's the less than, and there's the not equal to. And again, wherever our test statistic is. So this is assuming this is t, that's technically negative t, there's negative t and t right there, okay? Now, it could be in here, okay, for the test statistic, or it could be way over here for the test statistic. It's just a matter of where it is for that particular problem, okay? So in this problem, our test statistic, again, we had an X bar of 96, okay? So again, the formula looks like this. Our X bar was 96. Our mu, which is the hypothesized mean, was 90. Our our S was 23, and our N was 50. Now, I'm going to make one little edit to this. This is oftentimes written like this, where I would say this is a T with 49 degrees of freedom. And so you'll see this every once in a while where it's in parentheses like that. This is the degrees of freedom for this. It's just telling us what T curve we're going to use. It's the T curve that has 49 degrees of freedom, which is a fair amount, and one that we can then say is getting closer to a Z at that point versus like 2 degrees of freedom, which you'd have if you had a sample size of 3, which is going to be a little less accurate. Now at this point, the easiest way to approach this is to go to your calculator and go to stat test t-test, okay? You could calculate this out without going to t-test, and then you'd find the area to the right by using a tcdf function, okay? But the easiest route is going to be to go to t-tests. We're going to keep it on stats because we've got all the numbers here. We don't have a list of numbers from individuals. The mu is 90. The X bar is 96. The S is 23. The N is 50. And we have a greater than alternative. So we're going to use the one on the calculator that looks like this. This is meant to be the 90 there. So what it's really saying is your mu is greater than 90. And so we calculate. And what happens then is our test statistic here is approximately 1.84. So if we have the curve, our test statistic ends up being 1.84. And because it's greater than, we're going area to the right. So if we used a TCDF, we'd do 1.84 to 99, and then we'd put in degrees of freedom. So this is lower bound, upper bound, degrees of freedom, okay? And what ends up happening is this value now is 0.0356. So again, by definition, that means there was a 3.56% chance of us obtaining a sample of 96 or bigger, assuming that null of 90 was true. Now, obviously, we got a lower probability here. It's below 5%. So at that point, we have to judge really one of three occurrences. One is we didn't take a random sample. Well, the question already says we did, so we're good there. So we're basically left with either we're going to reject the 90, which happens in the next step, or we have to accept that we just got a rare sample. Well, we don't get to judge really the rare samples until we do more work on this. And so what we go with here is basically that we're going to reject that the actual amount of time students spend is 90 minutes. And that's where this final step comes into play. So again, sorry, it got cut off here, but based on our evidence, which is the p-value versus 0.05, we are going to reject the null hypothesis and say that we do have evidence that it's greater than 90. So our conclusion would look like this. Based on our evidence, and in this case it was a p of 0.0356 being less than 0.05, we reject the null hypothesis. And again, it's because when p is low, reject HO. And so when p is less than 0.05 here, we get to reject. So it's evidence, this is decision, and by rejecting the null hypothesis, we are saying now, and this is perhaps the most important part, so there is, and I'm going to actually say statistically significant evidence. You can leave that out if you want to, but that's just it's a good habit to write it because that's what really it means here. There is statistically significant evidence to support the alternative hypothesis that MHS students spend more than 90 minutes per day on social media. Now, it's very important to note, we aren't claiming what that number is. We aren't saying it's 96 because that's what our sample was. We aren't saying it's 100. We aren't saying anything except that it's more than 90 because we found evidence for HA. So again, if that had this been above 0.05, we wouldn't have that evidence, okay? And we'd just say we failed to reject, which means we're not saying it's 90, but we're saying we don't have the evidence to show it's anything other than 90 yet. Maybe we'll find that eventually, but at this point, we don't have that evidence, and so we have to roll with it. Again, the burden of proof, again, the idea like a courtroom, to find somebody guilty, we need to find that it's a low enough probability that it was anybody else, just like this. To find that it's anything other than 90, we need to get something that's a low enough probability to suggest it has to be something different than 90, in this case, more than 90. Okay, so that's what our evidence is for here. Now, what we'd want to do, of course, is probably run this again with another sample to kind of confirm our results. But right now, we have evidence because of our p-value from our sample of 96 with our standard deviation of 23 that we think, and our sample size of 50, sorry, that we think that students spend more than 90 minutes on social media per day. MHS students, that is. Make sure to keep that MHS students in there because you can't change your population midstream. So make sure you include that in your conclusion. Just be specific, write that complete sentence, and hope this helps. Thanks for watching, and as always, ask questions if you have them.